to this computer. And all right. So again, we have done U substitution, by parts, and trig integral so far. The next logical step is to then try trig substitution. Let me just check and make sure that's not someone else having trouble getting in. Yeah, there we go. All right. So trig substitution. Notice there's a nice little nifty chart given to you here on this packet. And that chart is just an indication as to what you should use. Now, you see that on the left, it says the expression, so what you would see inside the integral. So typically, these substitutions are used when you see radicals. But that is not the only time that you use them. You don't have to have a square root or a cubed root or any kind of radical to use this technique. You just need something of the form a squared minus x squared, a squared plus x squared, and so on. So what I wanted to do before I solve the first problem. So notice this first one up here says if we have something of the form a squared minus x squared, that we should let x equal a sine theta. So what happens if I do that? Well, I have a squared minus a sine theta quantity squared. And if I square that out, then I get a squared sine squared. They both have an a squared in common, so I'm going to factor that out. And you should see that when I do that, 1 minus sine squared is one of those Pythagorean identities. So after a while, you won't need this chart. You'll be able to say, okay, if it's minus x squared, well, then the Pythagorean identity is going to end up being 1 minus something squared, or 1 minus sine squared. Same thing over here for the plus x squared. Right? That means that your identity that'll be left behind would be 1 plus some trig function squared. Well, that Pythagorean identity is 1 plus tan squared. So what does 1 minus sine squared equal?
Cosine squared.
So if I substitute that in, if you want, you could rewrite it as a cosine squared. Well, then the square root and the square cancel, and you get back a cosine. So that's the beauty of this technique. It gets rid of that radical, right? Because that's the thing inside the integral that makes it disturbing, that makes it, you look at it and go, I have no idea how to do this with the techniques I've learned so far. And so using these substitutions allow you to get rid of it. So let me go ahead and demonstrate with the first problem here. So it says we've got an integral, we've got x squared and the square root of x squared minus 9 down there. So if I quickly scroll back up, looking at the options, the form I should use here is the x squared minus a squared. That's this one right here. Which means that I have to determine a and then let x equal a secant theta. So in this case, if a squared is 9, well, then a is obviously 3. So x in this case is going to be 3 secant theta. So any questions about why I chose that for this particular problem? All right. So I'm going to make a substitution for x, but if that's the case, I also have to substitute for dx. So dx in this case, right, I need to take the derivative of secant, that's secant theta, tangent theta, and very importantly, a d theta. Now, I'll tell you right now, the most common mistake with these types of problems is that people will not plug in for dx properly. They'll plug in the x everywhere, and they'll go, uh-oh, everything is theta now, so I can't have dx. I'm just going to rewrite it as d theta. So don't do that. So I'm going to substitute everything in here. For dx on the top, I'm plugging in 3 secant theta, tan theta, d theta, all that just for dx. On the bottom, I have x squared, so that is 3 secant theta quantity squared, and under the radical, I have to plug it in yet again. So then I need to start simplifying this as much as possible. And actually, one thing I want to do before I do that is calculate a triangle from what we have here. So let's do that quickly. And I say let's do it before because it's a good check to make sure that you've done the right thing, made the right substitution. So I started out by calling x equal to 3 secant theta. I can solve that for secant theta quite easily. Secant theta is the same thing as 1 over cosine. So this relationship tells me that the cosine of that angle must equal the inverse, right? 3 over x, or the reciprocal, I should say. Knowing that, I can create a triangle, a right triangle specifically. I'm going to call this angle theta. So cosine of the angle, that is the adjacent side over the hypotenuse. So the third side of the triangle is the square root of the hypotenuse squared minus this side squared. Now, why in the world did I do that? Well, at the end of the problem, I'm going to have theta. But at the beginning, I had x. So I need a relationship to get back to x. The other reason that I did that now is a good check to make sure you chose the correct substitution is if one of the sides equals the portion of the integral that you didn't like in the beginning. If those two things match, then you've made the correct choice for the substitution. So we'll come back to that, and it's clear that we got x squared minus 9 under the radical. So that is the correct choice. So let's simplify this integral now. So this term and this term are both going to be 9 secant squared. Right? And then, actually, instead of rewriting the integral each time, under the radical here, I can factor out a 9, and that gives me secant squared minus 1. Anyone familiar with what that's equal to?
Tan squared?
That is tan squared, right? So that all becomes 9 tan squared. Or if you really want, you could write it as 3 tan all squared. So let's substitute that in now. So I've got 3 secant theta, tan theta, d theta, 9 secant squared. And then I have the square root of 3 tan theta squared. So let's start canceling now. I've got a 3 here, which will cancel with that 9 and make that 9 just a 3. I have a secant that'll cancel with one of these secants. This radical will cancel that square. So now I have integral tan theta d theta over secant theta. And coming out of the radical, I have a 3 down here. Just throw it outside. And coming out of the radical is 3 tan theta. So again, tan thetas cancel. And I am left with 1/3 integral d theta over secant theta. Well, that doesn't look fun. But we can use the fact that 1 over secant theta just means cosine. And that's not so bad. And I actually need a, sorry, I need a 9 there. Right, I got 3, 3. So this is 1/9 integral cosine. That's something that we know. That is just sine of theta. We need plus c. And we would love to be done, but we're not. We have to do one more thing. We now have to go back up to that triangle and say, okay, how does sine relate to x? So if I look at my triangle here, what is the sine of the angle? Well, that's opposite over hypotenuse, or the radical over x. And if you really want, then you can just throw this 9 down here and be done. So a lot of steps, but a lot of it is just simplification, right? There's a substitution that you have to make. And then after that substitution, it's mostly just algebra.
I have a question real quick. I missed. So I get most of it, but when you first did your substitutions and stuff, how did you get the 3 up top when we first started?
How did I get this 3 here?
Yeah, the 3 secant theta.
So the substitution, right? It's x squared minus some a squared. And so
yeah,
I pointed to this one up here, so we need to know what is a. And when we find out a, we place it in front of the secant.
okay, I see it now. Thank you.
Mhm. Any other questions? I really do wish I could see more of you, because a lot of teaching, I think, comes from being able to see facial expressions. So I can look at you sometimes and just say, they have a question, they're just too afraid to ask it. Let's see. So I'm just trying to decide which one of these I want you guys to try. I think I'll leave this one for you to do. Hold on, let me check and see what this next one looks like. Yeah, I'll leave this one for you. Let me just give myself a little note here that I'm leaving that one. Of course, the little red circle just came along for the ride. All right. So here's another one. It's got a square root in there. The only thing that looks different is typically the x squared is by itself. So any suggestions on how to fix this?
Would you be able to take the square root and then put it on the other side of the integral as a constant? I don't know if that's right.
Because of the minus sign there, we're not allowed to actually take the square root of any of those things yet. So there's really two main methods. One of them is to divide through by 25 and factor it out. But I want to try something a little different here and see if it works for you. What if at the beginning of this problem, I say let u equal 5x, because this thing is 5x quantity squared. And if u is 5x, then du is 5 dx. So if I make that substitution, the integral now looks like square root 4 minus u squared. And we'd have a 5 that we would put in with the dx, which means we need a 1/5 outside. And this would be du then. Everybody okay with that? All right, so that's using our u substitution that we had done before. So it's okay if it's not x, right? We can still use the method of trig substitution. So now we're looking for something that looks like a squared minus u squared, or x squared. So let's scroll back up. Looks like a squared minus the variable squared tells us to use x, or in this case u, equals a sine theta. So a in this case is the square root of 4, or 2, right? Because that's our a squared. So we're going to let u equal 2 sine theta. And that means that du would be 2 cosine theta d theta. So let's go ahead and make our substitutions. Okay, so for du, I'm plugging in 2 cosine d theta, and for u, I plugged in 2 sine theta. Everybody still with me?
Mm-hmm.
I know there's a lot of variables running around. Okay. So let's look at inside the radical here for a second. This would be 4 minus 4 sine squared, or 4 times the quantity 1 minus sine squared. Again, we know that 1 minus sine squared is equal to cosine squared. And we could rewrite that as 2 cosine theta quantity squared. So let's plug that back into the integral. Okay. Again, this square root and square will cancel. By the way, the little lip that I put on the end of my radical just means that it's closed, as in whatever follows is not inside. So we've got 2 cosine theta times 2 cosine theta. That's 4 cosine squared. And I'm going to pull that 4 out in front. So what do I have now? As in what technique would I use to solve this? Anyone besides Jay can answer.
Could you use trig integrals?
Absolutely, right? This is the stuff we did last time. So I need to replace cosine squared. So what do I choose for that? Do I want to use the Pythagorean identity, or do I want to use the double angle formula? Or sorry, the power reducing formula.
The power reducing.
Okay. So I've got 4/5. Then cosine squared is the same thing as 1/2, 1 plus cosine 2 theta. So these are going to cancel and give me a 2 out here now. And I can split that into 2 separate integrals. We know that the integral of d theta is going to return theta. The integral of cosine is going to give us back sine. And because there is a 2 inside, we're going to get a 1/2 in front. So, isn't there a way to, did we discuss there was a way to raise your hand on here? Or was that in Teams?
It's under reactions.
Okay. So, how many of you are good so far? Just one? Fantastic. Okay, they're saying, all right. Why does it only tell me one person raised their hand?
I'm good, thank you. You raise your hand by going to participants, and then that way. The reactions are different, so if they use the reaction, it's not going to show you a raised hand.
Gotcha. You're welcome to just chime in as well. You can unmute and say, I'm good if you like. I just want to make sure that before I do these next couple steps that you're following.
I'm good.
All right. So I'm going to take it that at least half of you are good so far. The other half is either not paying attention, doesn't know how to use the button, or is completely lost. And if you're lost, I would hope you would say something. All right, so first thing I have to do is create a triangle. Right, we did that earlier on last time. And I'm also going to use both relationships. This one here, this u equal 5x, and the u equal 2 sine theta. So if I eliminate u altogether, right, that tells me that 5x equals 2 sine theta. Or sine theta equals 5x over 2. If I have that, I can create a triangle. Okay, so I have sine theta is 5x over 2. Make the triangle. Sine is opposite over hypotenuse. And the third side then is going to be the hypotenuse squared minus the other side squared. And that's really good because 4 minus 25x squared under the radical is exactly what we started with, right? So that means all this time we've made the right decision for the substitution. All right, so now, first thing I want to mention is notice this is just theta. There is no trig function associated with it there. And I want you to listen up for this one thing. This is the only time that you may use an inverse trig function. So for theta, we're told, or we've come up with the idea that sine of theta is equal to 5x over 2. We can solve that for theta. That is the inverse sine of 5x over 2. So in the problem, this is what I will typically see. And I just got done telling you the only time that you can use the inverse trig function is for when theta is by itself. This right here is junk. Right? How many of you know what in the world sine of 2 times the inverse sine means? I'm guessing none of you. Okay, so the only time you can use the inverse trig function is when theta is by itself. For this one, we need to use some more trig identities. So, does anybody have an idea of what identity we can use for sine of 2 theta? And a good idea is to probably print out that trig sheet and unit circle that I gave you on Blackboard, because all these identities are on that sheet.
Maybe we can use 2 sine theta into cos theta.
That sounds good. Thank you. So it's equal to 2 sine theta cosine theta. We can read sine of theta and cosine theta off of the picture. So this is 2 times the sine, which we've already calculated was 5x over 2, and cosine of theta, which is the adjacent over hypotenuse, or the radical, over 2. Okay. So if you want, you can cross these and then plug this in over here. So this is 5x times the radical all over 2 plus c. And if you want, you can just make this divide by 4. And I'm pretty happy with that. So hopefully we see that this is a much better solution for that second part than the sine of the inverse sine. Now, of course, if this wasn't sine of 2 theta, you could use the inverse sine there. But that isn't the case. So it's best to use this trig identity instead. So any questions about that problem?
I just want to double check real quick. So when you're doing your triangle and you make the 2, the hypotenuse, and then the 5x, so you get that third side by squaring the 2 sides and putting them under a radical, and then you check to make sure it equals that original.
It all depends on which side that you're trying to find. So if you're trying to find the hypotenuse, you would square the 2 sides and add them together under the radical. If you're trying to find one of the sides, you would do the hypotenuse squared minus the other side squared onto the radical.
Okay, but you know, like when you're checking it, if it matches, that's how you know you did it the right
That
way.
means that you've made the correct substitution.
Okay.
And I suggest doing that earlier on just because, you know, we would have done all of this work and potentially used the wrong substitution. But and then you do this at the end and you go, oh no, I've got to go back and do it all over again. Let's see how many more problems there are here. All right, so I think I'm gonna skip the ellipse unless we have more time for that one. It's a fun problem, but it's one that we can discard if need be. I want to do at least 2 more of these, and I'll leave 2 of them for you to do. So then I'll probably give you a little break time in terms of, you know, you guys breaking up and working some problems on your own. And then we'll look at some partial fractions. So let me go ahead and do D, and then I'll do 1 in the next section for you. All right, so again, we've got a radical here. We've got x squared plus 4. So what trig function is a trig function squared plus 1 that equals another trig function? What Pythagorean identity is that? So your options are sine, tangent, or secant. Those are the ones we typically use here.
Tangent.
So yeah, tan squared plus 1, right, is equal to secant squared. And so we've got here, we want to let x equal, if a squared is 4, then a has to be 2. And we're going to let it equal tangent. And again, if you don't know where I'm coming at with this, you have that chart at the beginning of the guided notes to help you choose.
Do you want all of those to be memorized by the time the first exam comes, like the power reducing formulas and then those as well?
I will discuss that a little further when it gets closer to the test, if that's all right with you.
That's fine.
All right. So x equal 2 tan theta. Then what is dx?
Two secant squared theta.
What else?
D theta.
Right. Can't forget that guy. All right, so let's make all the substitutions. So out front, we've got x cubed. So that's going to be 2 cubed tan cubed. Then we've got square root of x squared. So that's 4 tan squared plus 4. And dx is equal to 2 secant squared. Good with all that. So you should notice here, we're going to get 4 tan squared plus 1. All right, 4 times the quantity tan squared plus 1 in there. And so hopefully that's now showing you why I decided, or how I look at the problem at the beginning. And I can see that that's what it's going to turn out to be, right? Tan squared plus 1. Tan squared plus 1, we said, was secant squared. So this turns out to be 2 secant of theta quantity squared. So rewriting the integral, I had 2 cubed, and then I have another 2 there, so that's 2 to the 4th. I have a tan cubed. I have the square root of 2 secant theta quantity squared. And then I have a secant squared d theta. So the square root and the square cancel. This 2 secant theta is going to come out. Another 2 is going to come out in front. If that secant comes out, it's going to get multiplied by secant squared. And we're going to have secant cubed. So again, we've used trig substitution on a problem that we typically don't know how to solve. And it's gotten us down to now a trig integral. So for tangent secant, I think I'm going to pull out one of each. This is going to be my du. And in order to get that as du, that means that this has to be u, or in particular, u squared, right? So u is tangent. All right. So we've just got to figure out what to do with this secant squared, right? So someone have a suggestion? Someone I haven't heard from today probably would be nice. And if you need some motivation, remember that I have that little caveat there at the end of the syllabus that says that your participation in class is something that I take into consideration.
Maybe the Pythagorean identity of secant squared equals 1 plus tangent squared theta, or x.
Okay. So this is 2 to the 5th. I have tan squared plus tan squared. All right. So again, this is now going to become u squared 1 plus u squared du.
I just have a question. I don't have the chart in front of me, but I thought that the derivative of tangent was secant squared x.
I think you're crazy. Are you happy now? No, I'm kidding. Here, you'll enjoy this. You ready? These are my, oh. Let me show it there. Hold on a second. How do I do this? I don't want to look at myself. 1, 2. There we go. So this is my paper where I've worked this out before. Okay. And I got to that point. And I just looked down at this and saw that I had u squared minus 1, u squared du. Would you look at that? All right. Uh-oh. Jay's got something to say. She leaned in. She looked. She can hit unmute. Let's hear it.
No, I was just looking at something on my. I have a split screen, so I was looking at something on the computer.
All right. Everybody good? Yes or no?
Yeah.
Thanks for the thumbs up, Hannah.
No problem.
All right. So now I just need to distribute the u squared, integrate, and then finally I need to get back to theta. And then after theta, I need to get back to x. So this is u to the 4th minus u squared du. Integrating, that's u to the 5th over 5 minus u cubed over 3. Plug back in. U is equal to secant of theta. So then we need our triangle. So originally, we let x equal 2 tan theta, which means tangent is x over 2. And you should know that tangent is opposite over adjacent. Which means this side is the sum of the squares, square rooted. Because it's the hypotenuse. That's good. That appears in the problem. All right, so we made the right choice at the beginning. So now we just need to convert. Let me go ahead and see if I can snag this guy here and take it along with us. So now we need to look at secant. How do we get secant? Well, typically we don't read secant right off the graph, but we do know that secant's related to cosine. Cosine is adjacent over the hypotenuse. And so secant is the hypotenuse over adjacent. So this is 2 to the 5th. Secant is the radical over 2, but we have to be careful, right, because this is to the 5th power. So that whole thing is to the 5th power. All divide by 5. Minus, plug in the same thing for secant again. All cubed this time, right, because it's secant cubed. All divided by 3. And plus c.
Doctor. Doctor.
Yeah.
So what's that little circle near the so like it's near the 2/5. Do you see it?
The cursor you're talking about?
Yeah, that. All right. Just curious. I thought that was part of the equation.
No, I'm not sure why that popped up, honestly. Probably
Alright,
something
well.
with the draw feature.
Yeah.
We okay with all that substitution? Because I'd like to do at least one more thing to simplify it. So if you take this set of the parentheses, right, the first one is to the 5th power. So you'd have 2 to the 5th in the denominator. And you have a 2 to the 5th on the outside. So if you distribute this 2 to the 5th, it'll cancel in the first term. So let me just write it out here. I'm going to rewrite this as x squared plus 4 to the 5 halves, because it's to the 5th power and it's a square root. Okay, so it's to the 5 halves. It is still divided by 5. And the 2 to the 5th on the outside is going to cancel with the 2 to the 5th that I would get from the set of parentheses. Then I would also multiply that 2 to the 5th by the other term. This one's going to be x squared plus 4 to the 3 halves, because it's to the 3rd power and a square root. It is still divided by 3, and this one has 2 cubed. So this would cancel with this and make this 2 squared. So finally, oops. Should look like that. So questions I get a lot are, why not leave that 2 to the 5th on the outside? Well, in this case, because another term had a 2 to the 5th in it and it canceled really nicely, it makes sense to just go ahead and get rid of it. So I know there's a lot of stuff in these problems. Right, there's a lot of substitution, there's a lot of algebra, there's a lot of trig. Not a ton of calculus. How are we doing so far?
So far, so good.
I'm going to do one more example for you. Hopefully I can get that done in about 10 minutes so that I can give you guys 20 or so minutes to try the other two. And then start partial fractions for today. So as I said, I'm going to skip this ellipse problem. I could probably post the solution to that if you guys like. Like I said, it's a pretty interesting problem. Takes a little bit of thought on how to set it up, but it's it works out really nicely. I'm going to leave this one for you, and I'm going to do this one. So these are called completing the square. How many of you have heard of completing the square?
I did it in high school, but if I'm honest, I can't remember what it is.
Okay. So the first time that I remember doing completing the square, sadly, was in I believe differential equations for the first time. And you should have seen it way before then, but that's the first time I recall doing it. And what it is it's a technique to factor. So these three terms here don't currently factor under the radical, but I can set it up such that I can produce a set of terms that do factor. So I'm going to take the middle term, which we call the b term. I'm going to take that number, divide it by 2, and square it. So -4 divided by 2 is 2. 2 squared is 4. Now the next thing I'm going to do is under here, I'm going to go ahead and factor out a negative sign. So that's going to be x squared plus 4x. I'm going to leave a space plus something else. And then I'll leave the 21 outside. Okay. Now, regardless if b was positive or negative, because I'm squaring it, I always get a positive number, right? So I'm going to make this plus 4 in here. But you have to realize that minus there really means -4. And when I complete the square, I'm going to add and subtract the same number. So technically I am subtracting 4 currently, which means I need to add 4 out here.
I have a question just to clarify. That 4x, does that 4 come from what you calculated, or does it come from the b term when you, like, does that make sense?
This 4 here is the same 4 that we had before.
Okay.
Factored out the negative.
Right. Okay, thank you.
And then this one is the one that I've calculated.
That makes sense. Thank you.
So this now looks like we have to factor the inside. Now, the nice thing about completing the square is it always factors as this guy. So this is going to be x plus 2 quantity squared. So let's check that really quick. First term would be x squared. Multiply the two terms together, that'd be 2x, and multiply by 2 again, that's 4x. And then the last term would be 2 squared, which is 4. So that looks good. And on the outside, I have plus 25. So now I'm going to say, let's see, before I called it A on my paper, let's not do that. Let's say, let's just use U, I guess. So let U equal X plus 2, the stuff inside the parentheses. So du is just dx. So let's plug this all back into the integral now. Dx on top is just du. And all of this was under the radical, right? So if I let u equal x plus 2, this is really square root 25 minus u squared. That then looks like something we're used to in terms of trig substitution. So now the question is, what do I plug in? So we need something that's going to be 1 minus a trig function squared. The Pythagorean identity that matches that is sine. So let u equal 5 sine of theta. Right, 5 because a squared is 25, therefore a is 5. Du here then is going to be 5 cosine theta d theta. So go ahead and make all the substitutions. Darn you, computer. All right, so this is now going to be 5 cosine theta d theta on top. On the bottom, both of the terms would have a 25 in them, and it's going to become 1 minus sine squared. So I just skipped one step there, right? I'd plug in u, I would square it, and then factor out the 25. And then this is equal to cosine squared. So the square root of 25 cosine squared, it's 5 cosine. And guess what? This problem's awesome, because all that stuff cancels. And I get integral of d theta. Whew, that's a toughie. All right, I get back theta plus c. Now I have a single theta there. That means that's the only time I'm allowed to use the inverse trig function. I need my triangle. I also need to use the relationships that I've created and get rid of u. Right, I don't need u. So I have that 5 sine of theta is equal to x plus 2. Therefore, sine of theta is x plus 2 over 5. And that's opposite over the hypotenuse. The third side of the triangle is the hypotenuse squared minus this other side squared. Now the question is, does that match what we had before? Well, yeah, look up here. We've got 25 minus u squared, and u is equal to x plus 2, right? So that's the exact same thing. So that's good. And so I just need Actually, I didn't really need to do the triangle for the answer, but it's good just to make sure we made the right substitution because I just needed the inverse trig, which I can just get right from here. It says that the inverse sine of x plus 2 over 5 is equal to theta. Anybody going crazy? Having a mental breakdown yet? Or we hanging in there? All right, so there's 2 problems that are left minus the ellipse that I would like you guys to break off into groups and try. That is the first completing the square problem. That's this one here, if you want to write that down real quick. And the other that I left behind was, I believe, B. All right. So I'm gonna go ahead and break you guys up into groups. Let's see how many rooms we do. All right, so let's break you guys up. Let's take, I don't know, maybe 25 minutes. I'll be popping in and out. Hopefully I'll see some faces. Certainly hear some talking going on. Use the whiteboards, work together. It's always good to pop in a room and everybody's muted.
I'm doing pretty good with the problems. I feel comfortable with what we've done in class so far.
Garrett, you alive over there? Hey, buddy.
Yeah, we're doing good.
All right, I'll come back in a few minutes, guys. See how you're doing.
It'll be opposite over hypotenuse. So when sine theta equal, so it's opposite over hypotenuse. Okay. Wouldn't it be 4 over x? Oh no. Okay, I got you. Okay.
Yeah, no, just because once you have sine by itself, it'll end up, you have to get rid of the 4.
I got you.
I just wanted to add in that d theta there.
Right. Right here?
No,
Okay.
yeah, I put it in there. Yep.
Okay. I got you. Oh, thank you. So it'll be some.
Cos theta into d theta that way.
Yeah.
Yeah.
Okay, good. Just checking. Cool. Sine theta.
So I think then we would be breaking down the sine theta. So
Yeah.
it's gonna be, I think, sine theta is equal to 1 minus cos theta.
Theta.
Hello. Hey, just so you know, my camera isn't working, so that's why I haven't had it on.
Okay.
As much as you'd like to see me.
Oh, I was serious
allowed.
about the, like when I can see students' faces. You know,
Yeah.
they might not raise their hand, but I can, you can tell when someone's confused. And so I can, say, hey, Dimitri, you look like you got a question there. Would you like to ask something?
Yeah, I've been trying to use mine, but I think I have a setting blocked, so I got to look into that after class.
Okay.
Yeah, like whenever I try, it just gives me like a camera thingy. So
It's called censorship.
obviously, I'm just too out there. Can't have that on the interwebs.
How are we doing on the problem?
I think good. Like for like the first one, it's almost exactly like the other one, like the last one that we just did. The dx over the square root of x squared. Is it like the same as the previous one?
What do you mean by previous one? The very last problem I just did?
Yeah, completing the square.
Yeah.
I believe it's the same substitution.
Okay.
I think I used sine for that one as well. Yeah, so it's the same trig function. It will come out a little different though. Completing the square one came out really, really nice. It was just d theta. This one's not so nice. So I'll say that if you make the right substitution and cancel everything appropriately, you should end up with sine cubed inside the integral. And then you got to figure out what to do with that.
You just cancel out the square root. Well, not square root, the exponent.
Right.
So it would just be
Yes. Okay.
May I just make one quick change?
of course.
I see that when you plugged in for x cubed,
X.
you cubed the sign, but you didn't cube the 4. Right? It's got to be the other way you could write it is
Wouldn't that be what's 4? Wouldn't that be
so won't let me erase
64?
something that someone else did. That's interesting.
Hmm?
I was trying to erase the cube there on the sign. It won't let me. I
The
guess 'cause
cube
it's
there?
not my annotation.
Oh, I talking about like right here.
Yeah, can you get rid of that cube there?
I don't think I can. No, I can't erase anyone else's work. Oh,
There you go.
wait, maybe I did.
I
Or-
got it. Don't worry
Oh,
about it.
Oh.
The other way you could write it is like that,
Okay.
and then you'll make sure that you cube the 4 and the sign.
So in this case, that would be
So it'd be 64.
yes. I think my little draw thing. So it'd be 64. Okay. So, but this would still be. So now it's correct. I just forgot to do the 4.
And then, yeah, I think you just weren't done with your next part here. You got to include the 4
Oh yeah.
theta d theta, right?
Mm-hmm. Oh, I even forgot the 16. Hold up.
Put this guy in there.
So this. Then yeah.
All right, so 16.
Hmm?
This here again. This 4 should have been squared.
Which this one?
Right here.
Okay. Oh, okay. So that'll just it'll be also
So you don't get this out of it, right? It would be the square root of
16 sine squared.
that.
Okay.
And then what does that equal?
So that would equal. Let me erase this. That would equal 4. Or wouldn't that be 16 cosine theta?
Cosine, yes, but the 16 comes out of
That
the
would be 4. That would be 4.
Yep.
Okay. So, like so. And
I like that you typed everything but the theta, because it's not
Yeah.
on the board.
Are we going in the right direction?
Yeah, it looks good. We just got to simplify it.
Okay.
So I think I'm just like now trying to put that in a triangle and see if that works. So
Okay.
I have to ask, what is the tapping?
The tapping?
Yeah.
What's the tap? Is there like a tapping noise?
Do you guys not hear it?
yeah, we hear it, but we don't know where it's coming from.
Sure, I'm sorry. I don't know what it. Maybe it's my speaker. If I turn off, if you guys turn off. Is that better?
Yeah.
Mm-hmm.
Oh, cool. Okay, sorry, that was my speaker because I connect my computer to my speaker. I have a question actually, Dr. Perkins.
Yep.
So I'm just going to show my work because that's easier. So like we're working on b, the x cubed over the square root of x16 minus x squared. And so like I'm at like this step. Sorry, it's going to take a second. So like I moved it over here and then I canceled out the 4s, like put it to the 1/4. And then we got, now it's like 1/4.
So hold on 1 second. Let's see, you got 4 sine cubed, then you had 4 cosine theta d theta, and then what did you end up with on the bottom?
Before I canceled out the square root or after I canceled out the square root?
Before is fine.
The square root of 4 sine theta squared. I didn't know if that was supposed to be a -4 or a +4.
What did you let x equal at the beginning of the problem?
4 sine theta.
Theta.
4 sine theta. Okay, so inside the radical, then it should have been. And again, I'll share mine as well for you to see it. All right, you should have had 16 times 1 minus sine squared, which is 16 cosine squared.
Okay. Oh wait, Dr. Perkins. Can you look at mine too? Like then we are confused. It's like
we
have like done with differently.
Yeah, so the denominator should have been 4 cosine, not 4 sine. I think you just forgot to make the change. That's all.
Okay.
Wait, so when I had the square root, so what I did 16 minus 16 sine theta squared, right? And then I did 16 parenthesis 1 minus cosine theta squared.
Okay, so why did you change it to cosine?
Because I thought that you could use the what's it called? I forget how you say it, like the parenthesis thing. So like yeah. So like sine theta squared would be 1 minus cosine theta squared.
All right, so let me just pull up the little whiteboard thing really quick. So what I heard you say was you had this, right?
Yeah.
Which should equal.
It doesn't matter, by the way, if the squared is on the sine or the theta, right? Like it means the same thing.
It's typically written between the two,
That way? Okay.
or you'd write it like that.
Oh, okay. Is it wrong? I guess I'll just try to learn to write it.
If you write it the other way, it kind of looks like it's this, which is something different.
So like back where we were talking about like what I have, so in that second step where it says 16 minus 1 sine squared theta, instead of sine, I put cosine. Because that's when I thought that, wait, yeah.
That's where your mistake was.
So that's where my mistake was, I see, because I changed it to cosine for some reason. I should have kept it sine.
And then the next step would have been to make it cosine.
So if I make this sine, and that's because of the thing I was talking about
Pythagorean.
before.
Yeah.
Okay.
It's Pythagorean.
Say it again.
Pythagorean.
Pythagorean.
The guy's name was Pythagoras.
Pythagorean. So then it would be 4 cosine theta squared that you plug into the bottom.
It would come out as a 4 cosine. Right, because this is 4 cosine theta all squared.
So then that stays. So then that cancels. Wait, hold on. I think I am. So like at the end for right, like I did that right, and then I plugged it back in, and then I have now 1/4 integral sine theta cubed d theta.
I had 4 to the third on the outside.
Oh wait, yeah, I forgot that was a thing. Hold on. 4 to the third.
Right, there's a 4 cubed that's coming from the sine cubed. There's a 4 with the cosine d theta. And then there's a 4 that comes out of here. So that 4 and the 4 that comes out of here cancel. And you have a 4 cubed left that goes on the outside.
Okay, so I have a question, Dr. Bookins. Can you tell me what I have done wrong in this? Because I'm like stuck at this point and I don't know how to move forward.
Let's see, you have minus cosine. All right, hold on a second. Oh, keep flipping the page over, darn it. So yeah, you have minus cosine plus cosine cubed over 3. Yep. All right, so now you need to draw your triangle.
Yeah, so
Substitute.
that's there.
So what does cosine equal according to your triangle? Remember SOHCAHTOA, right? So cosine is adjacent.
It's gonna be adjacent to, yeah, so it's gonna be square root of 16 minus x squared upon 4. Okay, so I just need to like substitute that in it.
Now you plug that in for cosine, but you need parentheses because it's cosine cubed.
Okay.
So you have to cube that entire thing that you plug in.
So if I cube the entire thing, then for the square root would be removed. But what about the other?
See, right, it's going to be
Oh, okay.
3 halves and 1/2 for the other one.
Okay,
and you have
got
to
you.
have 4 cubed, right? Because you cosine cubed means everything inside there has to be cubed. I just pulled the 1/3 out in front of everything.
Okay.
Or at least in front of that piece.
That makes a lot of sense. I think I was confused. At the one at the top, like when I did the x cubed, I forgot the cube before. Which like sort of messed me up too.
Yep.
All right. I'll work on the other one now.
Okay.
I just had a quick question on completing the square. Do you do b squared over 2, like b squared over 2, or quantity b over 2 squared?
I'm sorry, give me 1 second. I was typing a message and
sorry.
No, you're fine. I just, it went in one ear and out the other one. I'm sorry. Give me just 1
No
second.
worries. All good.
take another 5 minutes. Okay, go ahead. Sorry.
All right. So when you're completing the square, is the like little calculation b squared over 2 or quantity b over 2 squared?
It's the second one, b over 2, then squared.
Okay. We used like an like example where both of them were the same, so I didn't know which one was right. Okay, thank you.
How are we doing?
Doing all right. I got confused, not confused, but I messed up somewhere in the substitution for the second problem, and I lost the relationship between x and theta.
Of course, that's the one problem on my sheet that I didn't actually work out prior to. Let's see, you would take 6 divided by 2, so you'd add 9 and subtract 9 inside, right?
No, I'm doing the x cubed over, or the integral of x cubed over the root 16 minus x squared. That problem.
Oh, I thought you said the second one.
Oh, second one that you assigned, but I guess it's first on the sheet.
Gotcha. So you chose 4 sine theta?
Yeah.
For x. You wrote your dx?
Yep.
Substituted everything in, made sure to cube all the appropriate pieces, right? Like 4 cubed, sine cubed.
Yep.
Then, sorry, I have a hard time seeing the page and displaying it. Let's see, where are we at? Cancel out everything, which would just be the cosines. You should end up with sine cubed.
Yeah. But I have 4 to the 4th outside the integral.
You should have had a 4 that was a part of the dx and a 4 that comes out of the radical. Those two 4s canceled.
Ah.
And you had 4 cubed left.
Okay. Yeah. Okay. Seems like I
you
added
gotta
an x.
break off a sine and replace the sine squared with 1 minus cosine squared.
Yep.
And then I made a substitution. So I let cosine equal u, and du is minus sine.
Right.
So that's why I have a negative out front.
Okay.
Do all that.
Yeah, I'm with you. I did that.
And multiply through or integrate. Plug back in. So u is equal to cosine. So you get cosine cubed over 3 minus cosine. And then the last thing is to use the triangle, which is there. So when you use your triangle and you substitute back in, then you should end up with this at the very end as your solution.
Okay. I got like 90% of the way there. But lost it when I went back to relate theta to x. So I messed up in that. But I had everything else right, so.
Everybody else all right?
Yeah.
I think I'm going to visit one more group, and then I'll bring you guys back together here in about a minute. I'll start the next topic, and then I'll probably only get through maybe one problem. I'll give you guys a chance to try one today, and then if you want, you can also go back and finish the problem that if you didn't finish that one already, the completing the square.
All right.
Okay.
1 second. I just put like everything together on the top. You see what I mean? Like the
Yeah, so this looks good so far.
this is because I put together 64 sine to this 3 theta and multiply by 4 cosine d theta, and then so I can, but I don't know like where I go next.
Well, 1 minus sine squared is equal to cosine squared.
Okay, right.
And
Okay.
the square root of cosine squared is just cosine.
Because I also canceled 4 and 4 cancels here.
Yep.
So it's gonna be this multiplied by cosine. And then here we're gonna this one transform to cosine.
Yeah, that whole thing just becomes cosine.
Cosine theta?
Yep.
Okay, and then we have here cosine theta and here cosine. Wait.
Yep, get rid of both of those.
So this one and this one going away, right?
Yeah.
And so and I have
I think you can get a new page with this.
no, oh my gosh, I just got this computer. I just got this computer, Surface Pro, so I'm trying to okay, so it's gonna be, I'm just gonna put here, it's gonna be 64 sine to the 3 like this.
Yep.
And
you're gonna have an integral and a d theta in there.
d theta.
Yeah, and then the integral symbol somewhere. And now that's a trig integral that you have to solve.
Okay. Do you guys see like how I simplified this in different way?
Yeah, I see what you did. Yeah. Much easier than we were trying to do.
Yeah, because that was the first one. I just put like together on one on top. Okay. Let me work.
So have you guys looked at the packet for this next section? Pretty thick, right? A lot of pages. There's also a problem that's done for you in here in excruciating detail. So that's why there's so many pages. It takes up, I believe, 3 whole pages. So if you need an extra example, it's there. So how did everyone do on that last section? Good, bad, no clue?
We almost finished.
All right, so I really want to get at least one problem of this topic done. And then, I'll try to leave about 20 minutes at the end for you guys to go ahead and work a problem. And
Sure.
if you did finish the one before, you can certainly work on that. And again, I'll pop in and out and you can ask questions.
And the thing you're talking about, the packet, were you referring to guide notes 5, I believe it? Like rational expressions?
Yes.
Okay. Gotcha. And I'm looking now. Looks about right.
So
Doesn't
are
look too
we
far.
comfortable to go ahead and start the new topic?
Yeah.
Anyone else want to comment?
Yeah, I'm good.
Okay. So it looks like we maybe lost a person.
I thought we had 20. Now we're down to like. Actually, no, we're not. We have 19. Never mind.
Yeah, so we lost one person somewhere.
You can't save them all.
They got tired of hearing me. All right. So let me share this page. So I'm going to go ahead and do one of these examples because we're not going to do a ton of these for homework or quizzes or most likely even the test. It's just something that I need to show you. So the first part is using long division. And this is for problems where the degree of the numerator is greater than or equal to the degree of the denominator. So notice in both of these examples, the degree in the first one here is first degree polynomials, right? They're x to the first power. The second problem, we have a second degree polynomial over a first degree. So those both meet the criteria of equal degree or the numerator is greater. So long division is something that you, and I've asked students this before, I think you probably learned back in somewhere between 1 and 5th grade, right? So it's probably been quite a while since you've done long division. So what I need to do here is I need to take the quantity on top and see how many times I can get the quantity on the bottom to go into it. Now I really only care about the x's. So what I need to do is say, how do I make x look like whatever this first term here is? Well, in this case, that's really easy, right? Because to make x look like x, I would just multiply it by 1. Then the next step is to take that number, multiply it by whatever's out here, and write it right there. Then I would also take that number and multiply it by -3, and that gives me back -3. Right, so I'm doing 1 times the entire quantity, x minus 3. And then the next step is to change all of the signs. So change this to negative and this to plus. And then you add down the columns. So x minus x is 0. 1 plus 3 is 4. The way you know you've done that correctly is if the first thing canceled, right, and gave you 0. So now I say, okay, how do I make x look like 4? Well, here's when you know to stop, right? If I can't make, if there's going to be an x in the denominator of the quantity, right, I have to make some number divided by x times x to get back a constant. So that tells me that I can't go any further. And so I'm just going to write this as a remainder. So now, instead of the integral that I was given, I am now going to integrate this combination. So the first one is just going to be the integral of dx. That's x. The second one, let's look at it a little further. Does anyone recognize what kind of integral that is, or what that would return?
Would be the natural log of x minus 3.
That is a natural log. So if you need, you could do a u sub, right? You could let u equal x minus 3, du, excuse me, would be dx. And then this would be du over u, which gives you back natural log. So real quick, right, I did this long division and I could see a couple faces looking at me going, I don't really remember this stuff. This looks weird. So just out of, what did we say? S and G's, right? If I take and try to put these two things back together, I would need a common denominator. To do that, I would multiply the first term by x minus 3 over x minus 3. And then you would add the numerators. So x minus 3 plus 4 gives you back x plus 1, which is what I started with. So that is the correct way to rewrite that fraction. And this is called a partial fraction decomposition. Now, of course, this is a very simplistic case, right? Maybe not so simple in terms of remembering how to do the long division, but it turns out to be really simple in terms of the integration. So I'll leave the second one for you guys to try, because I want to go over the rules for partial fraction decomposition.
Just a question.
Yeah.
Are we gonna have to show the work to get back to the original problem?
No, I just did that because I wanted to prove that, I decomposed it correctly.
Okay, thank you.
Mm-hmm. All right, so there are 4 terms here that we have to recognize. We have linear and quadratic, and we have repeated factors and distinct factors. Linear factors are what you'd expect. They look like the equation of a line. So notice these first ones here are linear. They're x plus 1, 2x plus 5, and 3 minus x. Those are all linear distinct factors. Now, why do we call them distinct? Well, we call them that because they only occur one time. And by one time, I mean that they're all to the first power. So you notice the next set says these are linear and repeated. So first, let's look at this one, right? X plus 1, that's the equation of something we'd expect for a line. It's to the second power. That's why we say it's repeated, because that is technically x plus 1 times x plus 1. So that is a linear repeated factor. The x cubed might be a little more strange to look at, right? Because you're thinking, well, that's a cubic function. But in reality, we're talking about factors. I can factor x cubed, and that's x times x times x. That's the same factor repeated 3 times, right? So that's called linear repeated. The third section here says it's quadratic and distinct. So when I say quadratic, right, notice the x term at the beginning is x squared. So probably the biggest hiccup here for students is the difference between an x squared term and something that's x plus 1 all squared, right? That's 2 different things. The x squared functions are quadratic. The x plus 1 to the second power is a linear repeated. Then again, these are distinct because they're all to the first power, right? And then finally, we have quadratic and repeated. So they're quadratic because they have x squared plus something else. And the whole thing is to another power. So that's repeated. Do we feel that we understand the difference between linear and quadratic, distinct and repeated?
Yes.
Anybody have a question about them?
Would it be possible for us to have one where it's quadratic and repeated alongside a linear one as well?
Yes, you can have combinations of factors. All right, so if we understand what they look like, now we can talk about how to deal with them. So for linear distinct factors, we just put a constant over each one of the factors. For linear repeated, right, we said that x cubed was x times x times x. So we start with a single factor, x, then we go up to 2 of them, x squared, and then finally as many as we possibly can, which is x cubed. And each one of those, because they are linear, only require a constant above them. So again, x plus 1 was a repeated factor, so we start with a single one, we go up to x plus 1 squared, and we just need a constant on top. So that's the difference between distinct and repeated for a linear type. If we then go on to quadratic forms, right? If it's distinct, we still just put each one of the factors in the denominators, but now the form on top becomes ax plus b. So that's because of quadratic. And if we have a quadratic repeated, again, we start with the factor itself, x squared plus 1. But because it's quadratic, we need ax plus b. And then we keep going until we get to the highest power that's in the problem. So I know that's a lot to take in. So let me go ahead and start trying a problem and see if that makes some sense. There's another thing to note before I get started here. There's 2 main ways to solve for these coefficients, A, B, C, D, and so on. They are called the annihilator method and system of equations. I'm going to do both. You can choose which one you like best. I will tell you personally, I like the system of equations. The annihilator method's really nice in some situations, and in other situations, all it does is make you, it'll make you solve a system of equations anyway. So there's already this one that's worked out nicely for you. So I'm going to skip that one because it's, you know, it's all there. You can look at that on your own. And I'm going to do problem A here for you. So first off, I have to factor this thing, right? Because the whole point of rational integrals is having some factors to deal with. So x cubed plus 3x squared minus 4x. I can factor out an x. Then I need two numbers that multiply to -4 and add to 3. So what would those two factors be?
4 and -1.
Okay, so x plus 4, x minus 1. So now I've got 3 factors there. What kind of factors are they? So are they linear or quadratic? And are they distinct or repeated?
Linear distinct.
They're all linear and they are all distinct, which means that this integral has to equal a over one of them plus b over another plus c over the last one. All right. So, if I put all 3 of these things together, I need a common denominator. Don't try and reinvent the wheel. This is already the common denominator. So if I look at the first term here, a over x, the 2 factors that it's missing are x plus 4 and x minus 1. So I must multiply top and bottom by that. The next one is b over x plus 4. It is missing x and x minus 1. So put those in there. And then finally, this last term, c over x minus 1, is missing x and x plus 4. And this has to equal the original problem, which is 1 over x times x plus 4 times x minus 1. Darn it. Oh. Darn you, computer. Let's see if I can. Okay.
It doesn't matter the order that you put it in denominator, correct?
No. It's all multiplication, so you can put the 3 terms in any order you like. So all 3 terms on the left-hand side of my equal sign here have the same denominator, which means I can add the numerators together. And in fact, every single term in my equation has the same denominator, right? Which means I don't care about the denominator anymore. So I have a times x plus 4 times x minus 1, b times x minus 1, c times x plus 4, all has to equal 1. So now I got to multiply this all out. So this is going to be a times, this is going to be x squared. Then I'm going to get a times 4 times x. Right, so that was that term. Then I'm going to get minus 4ax. And finally, minus 4a. So just trying to conserve some time here, I skipped foiling that out and then multiplying. I'm just doing that all at once. This is going to be bx squared minus bx and cx squared plus 4cx, all equaling 1. I'm then going to put all of the squared terms together, all of the x terms together, and all of the constant terms together. And you guys might think I'm silly, but I typically draw shapes around terms that are the same, so I don't lose track of them. I got to check that multiplication really quick. I think I messed that one up. Let's see. I should have had ax squared plus, or say minus 4a. Then I should have had minus 1ax and plus 4ax. There we go. I guess I'll draw a really big triangle around this. So I keep that sign in there. Okay. So all the x squared terms are circled. That's a plus b plus c. Come on. Uh-oh, pen's screwing up. Come on, pen, don't fail me now. All right, that's all times x squared. And then, so these two are going to be 3a times x, right? So 3a. Then I have minus b plus 4c all times x. And minus 4a for a constant. Everybody with me so far?
Yes.
I've done absolutely no calculus yet. So compare the left and the right-hand side. There's an x squared term here. Are there any x squared terms over here? Doesn't appear so, right? Well, that tells me that the coefficient on the x squared term must be 0 for there to be no x squared terms on the right. So a plus b plus c is 0. There are also no x terms over there, which means that coefficient must be 0. Lastly, we have minus 4a, and on this side, a constant of 1. Well, minus 4a is also a constant, so those two things must be equal. This is the system of equations that I then have to solve. The last one's really nice because it just tells me a is negative 1/4. So then what I'm going to do is I have a already, and I notice the two equations that are left have a in them, and I can eliminate b or c, giving me the other term in terms of a. So I notice I have plus b and minus b in the two equations. So if I were to add the two equations together, then I would get 4a, the b's would cancel, and I would get 5c. Solve that for c. I get minus 4/5 a. So that's minus 4/5 times a, which is minus 1/4. That's 1/5. And then I just need to find b. So I'm going to go back to this equation and say I've got b is equal to minus c minus a. Plug them in. And that gives me 1/20 for b. So I'm sure you're sitting there going, man, it's an awful lot of algebra. I thought this was calculus class. Well, we can finally take those three things and plug them back in to what we had above, which was this integral up here. So that integral is now going to be a, which is minus 1/4, right, over x. Then we need b over x plus 4. That's 1/20. And then finally, we had c over x minus 1 from above. Now, these are all really nice integrals because a, b, and c are constants. We can pull all of them out in front, and each one of those integrals is a natural log. So this is going to return 1 minus 1/4 natural log x plus 1/20 natural log x plus 4 plus 1/5 natural log x minus 1 plus a constant. And if you get there, I am ecstatic. You could technically put all three of those logs together. It's a mess. Don't worry about it. that's your final answer. So I wanted to do one more quick thing with this problem. I'll give you guys one to try, and you can finish up the other problem from earlier if you want. But I did mention that I was going to do both the system of equations and the annihilator method. So this was the system method. And you're probably going to hate me after I show you the other one. So let's come back up here.
I have a quick question. For
Yeah.
the tomorrow, is it going to be on this and trig substitutions, or just trig substitutions?
Did you say what are the quizzes going to be on?
Like the quiz tomorrow, do we have two, like one on trig substitutions and one on this, or just trig substitutions?
I'll most likely just give you trig sub because we only did one problem of this.
Okay, just checking. Cool.
I won't ever give you a quiz until we've finished the material for that quiz.
Okay, awesome. Yeah. Thank you.
Mm-hmm.
Is that going to be the first thing we do for class on Tuesday?
The quiz?
Yeah, like last time.
I'm probably just going to give it to you as due for tomorrow morning.
Oh, okay, cool.
Yeah, it seems like we're going to need as much class time as possible. So, and I'd like to get you guys broken up into groups and working. So to maximize that time, I think it'd be best just to give you the quizzes as take homes.
Okay, thank you.
All right, so real quick, eliminator method. We go back to this equation here. So say we don't know what A, B, and C are yet. The annihilator method says choose a value of X. That's a clever choice, and you'll be able to find A, B, and C very easily. So notice that the first two terms here have X minus 1 in them. So let X equal 1. What happens to both of those terms? They're going to go to 0, right? So if you block those out, then you just have Cx times x plus 4 has to equal 1. Or in this case, C times 1 plus 4 has to equal 1. 1 plus 4 is 5. That tells me C is 1/5. Make another clever choice for X. I see that there are two terms, both the B and the C term, that have just X in them. If I let X equal 0, the B and C terms will go to 0 and disappear. And I have A times 0 plus 4 times 0 minus 1 all have to equal 1. So that's going to be negative 4A equals 1, or A equals minus 1/4. And then the last one would be let X equal negative 4. That'll eliminate the A and the C term. And that'll give you B. It'll be 4 times 5. So B is 1/20. So in this problem, the annihilator method is really nice, right? It keeps you from having to do all of the system of equations portion. But in other problems, not all terms will cancel out. And therefore, all it will do is produce a system of equations that you still have to solve. That's the only reason that I'm more a proprietor of just doing this system anyway. All right, let's say you guys try B here for the last few minutes of class. We don't have a ton of time, but I'll stick around for a few extra minutes if you guys want to work on it. This one's not too bad. Only took me about half a page of work to solve it. So get that jotted down. I'll break you guys up into your groups. And I'll be popping in and out. I'll give you a quiz today. It'll be on trig substitution. Give me till, maybe Friday night to have quiz 2 and 3 graded. I'll put those up and return them. Another thing I wanted to mention real quick was if you haven't already started to do it, when you turn in your quizzes, please make the title of the file your last name and the quiz number. Otherwise, when I download it and then I got to type in your name and quiz number and then open it. It's just a lot quicker. And then I can sort them and send them back. I think that's everything. Anybody got any other questions for me before I break you up? All right.
Can you post the updated syllabus to the website? Because the one we have is from January.
The original one, I think, was a mistake. I thought I put up a different one, but I'll put up the most recent one that as I change it each time.
Okay, thank you.
Mm-hmm. All right, so I'm going to go ahead and just hit stop recording for now.